welcome to Sunday's edition of Cracking the Cryptic, where today we've got something which should be very interesting for you to have a go at. This puzzle on screen is called The Cross, and it's by Tom One Eye. I don't know if that's meant to be Tommy, but Mark's been looking at this in some detail, and apparently it is an absolutely staggeringly brilliant puzzle, but also quite difficult. I don't even know if Mark managed to finish it, but he has said I should have a go at it, and I need to highlight the big cages apparently, which I forgot to do before I started the webcam, so I shall do that now. Maybe this will reveal why it's called... Oh yeah, it does look a bit like a cross, doesn't it? Looks like quite an artistic cross we've got going on in the middle of the grid, so that's very beautiful. Anyway, yeah, should be difficult, and we shall see how things go. Now let me get rid of the highlighting. I've got some things to mention before we kick off today. Thank you so much if you joined me on Friday night. Was it Friday night I did it? It was Friday night. I know I lost track of the days. I apologise for saying the wrong day in yesterday's video where I tackled Shy's puzzle Pato Pato, but yeah, thanks so much if you join me on Friday for what might be the last stream I do of The Witness, because I did in fact reach the end of the game, and well, the end of the game was a bit perplexing for me, I have to say. If you've not played The Witness, I probably better not say any more, but there were certain things left unfinished in my mind. And thank you so much to those of you who've been trying to explain the ending to me. Anyway, we are taking advice on what we should do next. Whether it's that I continue to find other puzzles in The Witness, or whether we try a game called Bubba Is You, which seems probably to be the most popular one we've had suggested so far, along with the return of the Obra Dinn or something like that. And I need to say thank you actually to Jan Gunter, who incredibly has sent us a whole number of keys, basically, for Bubba Is You, for us to give away. So look out for that in the future. If you don't own Bubba Is You, there might be some opportunities to win the game on the channel, which is rather exciting. So again, huge thanks to Jan for that. What else do I want to mention? Tomorrow is the deadline for getting your solutions to the Looney Tunes Sudoku hunt to us. So if you want to be in with a chance of winning the merch, please send in your answer toot sweet. And also have a look out for Mark on Tom Scott's new channel. Tom Scott has just started a second YouTube channel. I think it's already proving very popular, and in one of the first videos on that channel he plays a game of Skull with some of his friends, Mark included, so do look out for that. There's no money on the line, but it's very interesting to see Mr. Goodliff giving it his full attention. So I'll try and remember to put a link under the script, under the video, if you'd like to check out that video. Lot of videos in that sentence. Right, now with all that said, let's get on to The Cross by Tom One Eye, and I will read you the rules. Here we go. Normal Sudoku rules apply. In cages, digits must sum to the small clue in the top left corner of the cage, if given. Okay, so the big cages don't look like they've got clue numbers, but they are each 9 cells large, and that's interesting if the rules say, and they do, digits cannot repeat within a cage. Okay, so there is something we should know about all of these red cages now, if we think about it. Clues outside the grid give the sum of the digits along the indicated diagonal. Digits may repeat along such diagonals if allowed by the other rules. So it looks like we've got normal little killer rules. So this 55 clue here is telling us that those 9 cells down this diagonal add up to 55. And we can repeat digits, so we could do something like, I don't know, 999. That would be fine. That doesn't seem to break the rules of Sudoku. It doesn't seem to break the rules of Killer Sudoku. So yeah, we can repeat digits as often as we like. Although those two could, for example, could not be 9s, because that would break the rules of normal Sudoku. Don't do that. It'll be wrong. Do have a go. The way to play, as always, is to click the link under the video. Now I get to play. Let's get cracking. And we shall start by... Well, maybe we should start by thinking about the 9-cell cages, actually, because although there's no total given for these cages, we do know what each of these adds up to, because we can't repeat a digit in a cage. And if these are 9-cell cages, and they are, then they must contain each of the 9 digits from 1 to 9, and if you add up those digits, because of the secret, you get 45. So each one of these cages could have had a 45 in its top left-hand corner. But I think probably not unreasonably, Tom One Eye thought we should work that out. Now, I'm just wondering about the central column actually. We've got 28. So those 3 squares there, because of the secret, if we think about column 5, all of the digits in column 5 will add up to 45. Those 6 cells add up to 28. So these 3 cells add up to 17. And unfortunately, that doesn't mean much to me. So let's look for something else. All of the little killer clues, we've got a 14 little killer clue in 2 cells there. So that's either 5, 9 or 6, 8. None of the other little killer clues look very useful at all. I'm almost wondering about combining the 7 and the 11. Not just because it gives you an opportunity to say the name of a shop. I don't even know if 7-Eleven shops still exist, but they used to. But if we combine those clues together, you can see this W pentomino here. That's got to sum up to 18 using five different digits. So it must have a 1 in it, and it must have a 2 in it. And we can tell that because let's imagine there was no 2 in this W pentomino. What would be the minimum it could sum to? Well, 1 plus 3 plus 4 plus 5 plus 6 is 19, and we need it to add up to 18. So there must be a 1 and a 2 in there. Yeah, okay, but we could actually have the 1 and the 2 on the 11 diagonal. That would still work. We could do 1, 2, 8 on this diagonal and make the 7 a 3, 4 clue. So it's not necessary for there to be a 1 and, well, a 1 or a 2 on the 2 cell 7 diagonal. Right, so what on earth? The 55 presumably is not... No, I don't think it is. I was just double checking in my brain that the 55 is sort of instantly dismissible because if you think about, there are 9 cells on this diagonal. So 55 divided by 9 is very close to 6. Now, knowing that the average cell along here is a 6 is very marginally interesting in the sense that the average digit in a Sudoku is a 5, but knowing that each of these digits is slightly high is nowhere near enough to know how they are filled. So I am a bit stuck here. I'm wondering if it's geometry we've got to think about, because these cages are very oddly shaped. Yeah, I mean, what it makes me want to do, if I actually, why don't I highlight them again? If I highlight them in orange, it makes me want to compare these orange cells with these 2 columns and these 2 rows. Let me just highlight that and take a stare at it for a second. Yeah, that might actually be interesting. We've got some double counting going on, which might complicate matters. So these squares in... yeah, this is definitely interesting. It's at least worth consideration. So we will look at this, I think. Let us... Seems to be a very common thing that we're doing on the channel a lot at the moment, which is this sort of set theory stuff, and I absolutely love it. Especially when, like this, it feels reasonably intuitive to go down this route. So what I'm thinking is the orange cells are 4 sets of the digits 1 to 9. Now let's make sure we all understand what I mean when I say that. This 9 cell cage here will definitely have all of the digits from 1 to 9 once each in it, once we've finished the puzzle. Now we have not got a clue, at least I don't have a clue, what the order of the 1 to 9 is in this cage, but we do know that it must contain each of the digits once each. So I can describe this cage as one set of the digits 1 to 9 in the finished grid. that's another set of the digits 1 to 9, etc. So the orange cells together represent 4 sets of the digits 1 to 9. Now, what we're going to do is we're going to compare this with, how would we describe column 4 of the grid? If I highlight all of the cells in column 4, clearly that is one set of the digits 1 to 9. Again, imagine we had the finished solution to this puzzle. In the blue cells, we would now have one set of the digits 1 to 9. If I highlighted the whole of column 6, I've got another set of the digits 1 to 9. Now, this is where it gets a little bit more complicated. I want to highlight the whole of row 4. Now, if I highlight the whole of row 4, that will be another set of the digits 1 to 9. But look out here, because this cell was already included in column 4. So if I do highlight all of the cells in row 4, because I want another set of the digits 1 to 9, this cell, whatever is in that cell, and indeed whatever's in this cell, because this was in column 6, these two digits appear twice now in the blue cells. So I'm going to give them a little purple flash to say these two cells have appeared in blue twice. Whatever that digit was, if it was a 6, then this 6 in the blue set should be duplicated so it appears twice. So I cater for the fact that I've got it once from column 4 and once from row 4. Now, finally, I want to do the whole of row 6. Now that's our fourth set of the digits 1 to 9. And again, this cell was in column 4, this cell was in column 6, so those two get a purple flash. Now, at this point, I want to be very precise. It is true to say, because the orange cells were 4 sets of the digits 1 to 9, and the blue cells, counting each of these cells twice, are also 4 sets of the digits 1 to 9, the orange and the blue are equal. They contain exactly the same digits. Now, let's look at this cell. This cell is both blue and orange. So what would happen if I removed the digit that appeared in that cell? Let's say it was a 5. What would happen if I removed 5 from both sets, both the orange and the blue? Would it change anything? Of course it wouldn't. The orange and the blue sets would still contain the same digits because I'm removing the same thing from both of them. So, any cell that is, Maverick's just taken off, I don't believe it. Any cell that is both blue and orange can be removed from both sets. You can see there are a lot of these cells here. All of those cells we can just delete from both sets. Now let's think harder about these cells here. Remember, these cells were double blue, but they're also in orange. You can see that they've got an orange flash and they have this sort of double blue flash represented by the fact I introduced purple to them. So if I was to remove this digit, let's say it's a 6 again, if I remove this 6 from orange and blue, because it was double blue, it will still remain blue. So these squares here all need to just be the colour blue. And this is what I could see when I did the highlighting originally. And this looks interesting to me because something I definitely didn't know at the start of the puzzle is that the orange cells, because we now know that the orange cells and the blue cells are equal to one another, the orange cells here must all be different digits, because these blue cells must all be different digits. They're all in box 5 of the Sudoku, so they can't repeat. And my phone is buzzing at me, and this means I must check who it is that's buzzing me. No, this is fine. So these orange cells are all different. Which means what then? Not sure immediately. Let me just think about this for a second. They are all different digits. So there's got to be some way. Oh no, I know what it is. I know what it is. This is really clever. This is really very clever. Let us look at the diagonals now that include the orange cells. This is a 10 diagonal. This is an 11 diagonal. This is an 11 diagonal, and this is a 10 diagonal. Now there is one digit that no matter how much I might want to, I cannot include on any of those diagonals, and that's the digit 9. I can't put 9 on an 11 diagonal because I'll have to put double 1 alongside it. And I can't put 9 in a 10 diagonal because then I'll have to put even sillier digits with it. So there just can't be a 9 in orange. And if there can't be a 9 in orange, that tells us what the middle digit of the Sudoku is. Because if you can't put a 9 in orange, orange must be the other 8 digits. So they form that loop, and that square there is a 9. That is absolutely beautiful. It's completely crazy, but it is also very beautiful. Now, so that means I've got to put... Right, okay, so now I must have an 8 in one of the 11 diagonals, because I can't put 8 on the 10 diagonals, because if I do, I'll have to put double 1 with the 8. Oh, so this probably is 812 then. That would work with the 11 diagonal. If you put the 8 over here, the 8 would go in one of the orange squares, and you'd have a 1-2 pair in the other 2 squares. So that would mean you couldn't have... Oh, this is confusing. I'm almost going to have to keep a track of what digits I've put in orange. Because I'm thinking if I put 8 on this diagonal, I'm using up a 1 or a 2 in one of those squares in orange, which means over here I couldn't put that digit. Let's say it was a 2 in that square. I then couldn't have a 2 in either of those squares, or indeed in any other orange. Now, what does that mean? I'm not sure. The other thing I'm tempted to do, though, yeah, I'm wondering about trying to use the secret on the diagonals again, because we know that the whole of box 5 adds up to 45. 45 minus 9 is 36. And I know, therefore, that those orange squares in these diagonals here add up to 36, so I should be able to work out the value of those 4 squares. 10, 20, and 22 is 42. So the whole diagonals add up to 42. The orange squares add up to 36. So that, So the 4 squares I've highlighted, which have to deal with the difference between 42 and 36, add up to 6. And so in order for these digits to add up to 6, they've all got to be, well, you've got to put a 1-2 pair in there and a 1-2 pair in there. That's the only way it'll work. Or you can think about it this way if you prefer column logic. That must be a 1-2 pair adding up to 3. That must be a 1-2 pair adding up to 3. So that's... Oh. Yeah, oh, this is lovely. Right, now have a look back over here, where we'd labelled 1s and 2s into our W pentomino. Well, that square can't be a 1 or a 2, as it sees a 1 or a 2 in its row, and that square can't be a 1 or a 2 because it sees a 1-2 pair in its column. So that you can't put a 1-2 on the 7 diagonal, so the 7 diagonal is a 3-4 diagonal. Now... Right, okay, well that... Yeah, and this is lovely, because that means, given the fact that we needed to put a 1 and a 2 in the W pentomino, the 1 and the 2 must now be in 2 of those 3 squares. So those 2 squares will add up to 3. The whole diagonal adds up to 11, so there is an 8 on this diagonal, which is what we thought. So these squares here are 1, 2, and 8. So now I've used the 8 So there's an 8 in one of those squares, which corresponds to the 8 that we must put in one of the blue squares. So there now can't be an 8 in any other orange cell. And there can't be whatever, whether it's the 1 or the 2, that can't go in any of the other cells either. Now, oh, I know what we should look at now. What about column 5? We had to make those 3 digits add up to 17. So these 2 digits now add up to 8, because we've got a 9 here. No, I'm not sure I can do that, can I? So maybe the thing to do is to think about 7 in the oranges now. Is that a sensible idea or not? I've got to put 7 in orange, but I could put it on a 10 diagonal with a 1-2 pair. That would use up all the 1s and 2s combined with the 11 diagonal using up the other one. If I put 7 on this 11 diagonal, I've got to put 1 and 3 with it. So this would have to be a 1, this would have to be a 3. Is that impossible for some reason? I don't know is the answer. This is still very tricky. I feel like I've done quite a lot of logic to this point. How long have we had? 22 minutes. I don't feel much closer to, oh, maybe the 55 diagonal. No, in fact, the 55 diagonal is looking rather average, isn't it? Because I've got 2 low digits and 1 great big digit. So these are averaging out to maybe a slightly low number, meaning the rest of it has to add up to a slightly high number. Doesn't feel like that's restricted. 1-2 pairs all over the place as well. So you can't put 1s and 2s in any of these cells. Let's just have a look at this. So none of those squares can be a 1 or a 2, which I don't know what that means. This is tricky. This is very tricky indeed. I wonder, if you do use 7, 1, 3 here, are you going to struggle to make 10 twice in these squares? Is that the point? If this was a 1, these 2 squares would both be 2s. Oh, I'm getting confused now. So if this was a 1, these 2 squares would both be 2s. This would be a 1. There would be a 2 in one of these squares. There would be a 3 in this square. And I could do 1, 2. I've used this. No, hang on. I'm using the 7 here, aren't I? So now I've got to use 6s, 5s, 4s, etc. and get up to the right total here. So I could do, but I couldn't use 3. I'm not sure you can make 10 twice doing this. I just don't think it works. If you do 1, 3 here and 2 2s there. Now, I've used the 7 here. So now how am I going to make those 4 digits there add up to, well, each pair here needs to add up to 8. But it's impossible because I've used the 7 and the 3. So there's only, in fact, it's utterly impossible. There are no options left to add up to 8. You can't use 2, 6 in either of these because the 2's already in the box. You can't use 1, 7 because 7's gone. You can't use 3, 5 because... So that is nonsense. Okay, that's actually a little bit interesting then. So if that's correct, 7 lives in one of these 4 cells. Which means it will be accompanied by a 1 or a 2 on its diagonal, which will go together with the 1 or the 2 in this diagonal. So this diagonal here cannot use 8, 7, 1 or 2 in its orange squares. So if this was a 1, these two would have to add up to 10. They could be 4, 6. If this is a 2, these add up to 9. Oh, they could be 3, 6 or 4, 5. This is horrible. This is so tricky. How does this work? It doesn't work at all. There's no way of resolving it. Maybe I have got to look at the 55 diagonal then. Is this more restricted than I realised? Maverick is flying ever lower in an effort to distract me, or an effort that seems to be working. Right, let's look at those 3 squares together then. They're going to add up to a maximum of 24. So that means these 6 squares need to add up to 31 or more. 31 or more. So can we rule out a double 1 here? Because that would mean that these 4 squares need to add up to 29 or more. I don't think that's difficult though, is it? What you couldn't do, let's just highlight these squares. What you couldn't do is put 9 and 8 into those 2 squares because that's going to break the 14 diagonal. So the best you'll do, the highest total you could make there would be 9 and 7. And the highest total you could make here is 9 and 8. And that's too many, I think. That means you've got 17 here and 16 here. If you were really trying to push the boundary, that's 33, and we needed 29, and we've comfortably got 29. So there are loads of degrees of freedom in the yellow squares. And that's what my suspicion was. So my suspicion was correct, but unfortunately that doesn't help us. And the expression that we look for in these trying times is bobbins. Oh no. Oh, I did so well to find this break in, I think. And now I've totally been flummoxed. I check these diagonals. There's definitely, I think, at least 3 ways of making this 11 diagonal work. How do we make more progress now? I've got to include 1 of every digit in orange. So whatever is in there, it's not going to be something to do with the fact that whatever's in these, the fact that we've got 8 in one of those means you can't put 8 in those cells. So that means 8 is a bit restricted in like column 6 and row 4, but not in a way that's useful because I don't know anything else about 8s in the puzzle. Ones and 2s, let's have another look at that. If we've got 1s and 2s in these, we can't put 1s and 2s in any of those cells. So no, I don't think that's doing anything to the 16 or the 12. It's not doing anything to the sort of outside cells in column 5, which have to add up to 8. If you could, yeah, that's interesting. If there's some reason that, let's just highlight these cells, which can't be 1s and 2s. If there was some reason these 2 cells couldn't contain a 1 or a 2, these would have to be 3, 5. I have no clue why that should be the case, though. That doesn't look right, does it? Ah, no, okay. Ah, I have something, perhaps. What about... Oh, yeah, okay. Oh, this is very, very beautiful. If this is right, this is really very beautiful. Let me just think about this. Hang on. I might have something here. And it is to do with the yellow cells. So, yeah, okay. I think I can get rid of some of the flexibility on this diagonal, I think. So what I'm thinking is, where does this digit, oh, I shouldn't use blue, let's use purple. Where does this digit go in boxes 1 and 9? And in particular, is it possible that this digit doesn't go on the 55 diagonal in one of those 4 squares? And I don't think it is possible, is it? Because in this box, let's look at this box first. I've got a choice of exactly 4 cells where the purple digit can go. It could go here or here on the 55 diagonal, or it can go here or here. Now, if I want to keep this digit off the 55 diagonal, I've got to put it in one of the orange squares. Now, if I put it in one of the orange squares, it can't now go. It can't repeat in an orange square. So in box 9 now, you can't put it in an orange square. And if you can't put it in an orange square in box 9, where does it go? It has to go on the 55 diagonal again. So this digit, which is a very low digit, needs to make at least one appearance in one of those 4 squares. And if that's true, my count for the 55 diagonal was utter rubbish, because I assumed I could put like 9s, 8s and 7s into those 4 squares, which I don't think I actually can. So now I'm going to do this again. If we go max these out. Now, is it actually possible now for these to be double 1? If these are double 1, now I have to put a 2 in one of those 4 squares. Now let's try and put the 2 in the optimal square so we can maximise the other digits. We still can't put 9 and 8 here. We can put 9 and 8 here. So yeah, okay, so we should put 9 and 8 there. And then I could put 9 in one of these squares and 2 in the other. And that's the highest I'm going to get to, isn't it? That still allows the 14 to be filled. So something like that, I believe, is the highest way we can fill the 55 diagonal with double 1 in those squares. Now, what does that add up to? 10, 12, 20, 29, 36, 40, 54, that's it, 54. That's not 54. Here is the knowledge bomb for cracking the cryptic. It's not the same as 55. So this cannot be true. You cannot make this diagonal add up to 55 if you put double 1 into those 2 squares. And that means, let's unwind that therefore. Well, firstly it means that must be double 2. Now that must be double 1 by Sudoku. You've still got to put a 1 on this diagonal. Now let's just double check this is going to work now. I think it should work, because we've gone from a total of double 1, 2 on the diagonal, which is 4, to double 2, 1, which is 5. So I think we're going to just hit 55 now. But we're still going to have to be a bit careful about this, because we're still going to have we still have to put a 1 in one of these cells. And if I put the 1 here, I can obviously make that a 9, but I can't 8, 9 those two, and that's not going to be enough, I don't think. That would be 9, 7. And I don't think that will add up to enough. Let's in fact just check that, just to satisfy ourselves. I think this is going to be one short. We've got 10, 20, 36, 45, and 9 is 54. Beautiful. It doesn't work. So that means that we're going to have to put the 1 in this, one of those two squares, along with a 9. So this is a 1, 9. This can be an 8, 9 pair. And we don't know the order of that 7 and 8, do we? Now, hopefully now, this will add up to 55. You've got 10, 12, 29, let's add the 7 on, 36, and 36, and 19 is 55. Beautiful. This is absolutely brilliant setting. It's brilliant. I'm going to just get rid of the yellow now because I think that that's going to distract me. Let's get rid of the purple and take a stare at the puzzle. Because what has this done for me apart from, well, it's given me 1s and 2s. Right, it's given me, I've definitely got a 2 in orange now. I've got a 9 in one of those squares, so this 14 diagonal has become 6, 8. Right, and didn't I think that I had to put a 7 into one of the 10 diagonals? And if I have to do that, it can't be this one anymore, because I would need 7, 1, 2, and I can't put 1 in the orange squares. Yeah, we did look at this. If you put 7, 1, 3 in there, here, you need these to add up to 8 and these to add up to 8, and there just aren't the digits available because you can't use 2, 6, you can't use 1, 7, you can't use 3, 5. So we did check that. So there is a 7 in one of those 4 orange squares. It can't be those two. So this now is a 1, 7 pair. That 11 diagonal is probably false now. Yes. It can't use 9, 8 or 7. That's 5 and 6. And that must be 3 and 4 to complete the box. There's a 3, 4 pair in row 2. I've now used 1, 7. I've used 1, 2, 7 and 8 in orange. 1, 2, 7 and 8. And there's no 9 in orange. So I now need to, these 4 squares are definitely 3, 4, 5 and 6. These 2 squares have got to add up to 8. There's only one way that will work. That's got to be 3, 5. That means those can't be 3, 5. This is a 4, 6 pair, and 4 plus 6 plus 1 is equal to 11. QED. This is ridiculous. This is one of the great puzzles. It's one of the great puzzles. That must be a 4 and a 7 to complete box 9. Now what can we do over here? We've got an 11 diagonal, which can't be 4, 7 or 5, 6. It can't be 2, 9 because you can't put a 2 on it. So that's 3 and 8, I think. 8 is now, where does 8 go? In row 7 of the grid. It can't go in any of those squares, so there's an 8 in one of these 3 positions. There are, look. There's a 1, 7 pair in this cage already. So that square there is an 8. And that must be the 7. That's not an 8. 8 is also restricted, I'm now seeing, in row 2. We've got an 8, 9 pair there, so it's not in those 3 squares. A 2, 8 pair there, so it's not in those 3 squares. So 8, in fact, must be in this domino here. No, 8 is not there, because that is a 2, 8 pair, and that's that square which is in its cage. So that's an 8, that's in the 16 cage, that's an 8. So now, oh, I see what's going on here. Right, now there must be a 4 in the 12 cage. Why do I think that? Well, if we think about the nature of column 5, we've got this domino here summing to 8. We've got this sort of toroidal domino. If we leave the top of the grid here and pop in at the bottom, we know those two squares add up to 8. So we've got an 8 toroidal domino, a real 8 domino there. There are 3 ways of making 8 in 2 cells, 1, 7, 2, 6 and 3, 5. So the other way of making 8 must live in the 12 cage, along with, therefore, a 4. That's the way I think about the world anyway. I know it's probably a bit strange, but never mind. Now, what else can we do? Have we done all of the little killer clues? I think we have. That's good and bad. It's good because we've done them. It's bad because the puzzle doesn't look to me to be in any way close to being finished. 7 is a bit restricted in box 4. This 7 combined with the 1, 7 pair means there's a 7 in one of 3 places, 7 in one of 3 places in box 6. Wow, okay. Good grief. I've not got a clue where to look, to be honest. I think I must have to... No, I really don't know. There must be something we can do that's just Sudoku here. 2. Okay, 2 is a tiny bit restricted in box 7, one of 2 places. I think there's going to be some alignment of digits between these various pairs we've got all over the place that we're going to have to use. But it's all very well saying that. I've actually got to... Oh, 7 is more... okay, 7 is quite restricted in box 2, I've just spotted, because it can't go in those squares or those squares. So 7 is in one of 2 places. Ooh. Oh, no, right. 2 things result from that, which are both quite interesting. The first thing I was noticing is that this 7 is part of the toroidal domino. So if this was a 7, you'd have to put a 1 here. But if this is a 7, this is part of a real domino adding to 8, so you'd have to put a 1 here. So the 1 in column 5 is either there or there. I admit. That doesn't seem to do anything. But I have spotted something else, which is that the 7s now, we should ask where 7 goes in row 2. It can only go in this cell. So that is another digit in the grid. That ooh, hang on. This is interesting. That 7 here now fixes that square. That's got to be a 4. That's got to be a 7. That's got to be a 7. Now, what does that mean? So that means... I'm just wondering if that's going to do something to where 7 is in one of those squares. So 7... I think 7 is in this domino in box 8. I'm saying that with I feel like that's far from certain, but I do think that is what it's saying. 7 in box 7 is also quite restricted now. It's got to be in one of those 2 cells. Ah, this is good. Yeah, this is good. So now, look at where 7 goes in column 2. It can't be in those cells or those cells, so it must be exactly equal to that cell. And that's another digit in the grid. So how many 7s have we got? We've got 5 7s. We've got 7s in one of those 2, 7s in one of these 2, 7s in one of these 2. Oh, and 7s in one of those 2. Okay. So they all look like they're sort of franking each other in a way that's quite unhelpful. Maverick. Okay. So, but the problem with this is still that I don't really see how to make much progress here. I've used all the little killer clues. I keep having to remind myself of that because I keep looking at them. How long have I had? 45 minutes. Good Lord, it's going to be another long video. Mind you, I was expecting that. I think this puzzle is apparently very difficult. I've got a 3-4 pair in row 2. So these squares have got to be from 5, 6 and 9. So there's a 5, 6, 9 triple here. That's useless. We don't seem to know anything about 5, 6s and 9s for some reason. So have we got anything else going on? We've got right, what digits have we got a lot of? We've got a lot of 7s. I've looked at 7s. We've got a lot of 8s. Well, actually, we haven't got very many 8s, but we have more 8s than other digits that are not 7. 8s. Ah, right, okay. I can do something with 8s, I think. Yeah, that's rather pretty, actually. This square can't be an 8. Why do I say that? Well, let's imagine it was an 8. The 8 in box 7 would go there. The 8 in box 9 would go there. And now I can't put an 8 in box 3 anymore, because this can't be an 8. Let's actually do it longhand. If that's 8, that's 8, and that's 8. And now look, neither of those two squares can be 8. And one of them definitely needs to be an 8. So that is progress. That gives me a 9 up there. And then 8 here. Oh, that would have been nice if it actually caught this 3-8 pair. Oh, this 8 does resolve my 8 and my 2. And that would have been nice if it caught anything down here, but it doesn't do it. Ah, no. There's a 2 in one of these 3 squares. Good grief. No, it's just stalled again. What do we need? We've got 9. Oh, I was about to say 9's interesting in box 3, but it's not. 9's in one of those 2 cells, but we already knew that the 9 in box 2 was in one of those 2 cells anyway. So what do we need here? This square's got to be a 5 or a 6. These are 5, 6s and 9s. 5, 6. Ah, right. This is really, actually, this is beautiful again. It's the same logic again. Look on this corner now. So we did it in this corner. I'm now going to do it on this corner with 6s. If that's a 6, that's got to be a 6, and this has got to be a 6, and that won't work because look where the 6s are in box 7. They're in those 2 squares, and now neither of them can be a 6. That's really, really beautiful. It's so simple, but I love the fact you can do it here and then you can do it here again. That's really, really elegant. So that's a 5. Ah, that I was about to say that's not doing anything, but that would have been maligning that 5 unfairly because it is doing something. It's giving me a 6 and a 5 here, which isn't doing much, but it is actually, look, hitting this 3-5 pair here. So that's a 5 and that's a 3. And that's a 3 and that's a 4. And that's a 3 and that's a 4. And pregnant pause. That means that I don't know. That must do something. I'm sure it's doing something. I just can't see what it is. There's a 4 up here now. Still don't think I know which of those is the set. Oh, I know that's not a 4, because if that's a 4, that's part of the toroidal domino. And in fact, we've already got a 4 pencil marked in there, reflecting that fact. So this now, no, this could be other digits, I think. Well, let's just check. 1, 2, it's not 4, so it's 1, 2, or 7. Now that means the toroidal domino counterpart is 1, 7, or 6. Disappointing. What about this square? Because this is also part of an 8 domino. That square there is 1, 3, 5, or 7. Is it really? Oh, it's not 1, because that would put 7 here, and there can't be a 7 there. So that's 3, 5, or 7. That's 3, 5, or 1. Which is really rather annoying. I'm trying to see if there's a way of resolving that. I don't think there is. Although, hang on a minute. That... Yeah, no, this is lovely. This is absolutely lovely. Right, let us have a look at this square here. This one. I'm going to give it purple colouring as a reflection of its magnificence, because this is a magnificent square. So the question I want to ask first is this a 3? And the answer is no, it's most certainly not a 3. Why, I hear you say? Well, the reason it's not a 3 is that we've got to put a 3 in this little thing here. It's got to be a 3 somewhere in it. Now, if that's a 3, the 3 would have to go in one of those cells. But look, it's the same over here by symmetry. You've got to put a 3 in this, and you can't put it here, so it's got to go there. And now I've got 1 3 in that string of digits and 1 3 in that string of digits, and that's 2 3s in box 2, and that's wrong. But the logic works the same on 5. Because you can't hide a 5 in any of the oranges, if that's a 5, you've got a 5 in that stripe and a 5 in that stripe, and that doesn't work either. You can't put 2 of the same digit in box 2. So that square, I think, has to be a 1. And that works because you don't have the same problem now. You can hide the 1 in this cage in one of those positions in box 1. So you get out of jail. And that means that square is a 7 to make that work. That one's 7, so that's now a 2. And the toroidal domino position is a 6. Sorry, brief interruption there when my burglar alarm went off, which is very peculiar given I am in the house and, as far as I know, I am not a burglar. Anyway, where were we? We were just getting... Oh yeah, I got the toroidal domino done, didn't I? So I got the toroidal domino done. And that means we've got a 7 here, which gives me a 7 and a 1 here. And we can... Well, there's a 1 in one of those 2 squares. The 7 here, look, is helping me in box 7. That can't be a 7 anymore, so the 7 goes in the corner. And that's a 7. Feels like we've done a lot of 7ings. We have done a lot of 7ings now. That 7 took the position of a 2, so that's a 2 in the corner of box 7 as well. 2 has to be in one of those 3 cells, I think. 5 means we've got a 6-9 pair in box 2. Those 2 squares have got to be a 3-5 pair. And these 2 squares have got to be a 1-4 pair, and that's lovely because there's a 1 already in this cage, so that square can't be a 1, that's got to be a 4, that's got to be a 1. 1 lives in one of those 2 squares in box... Oh, this is gorgeous, right. 1 lives in one of these 2 squares in box 8. Well, they see that square, so that can't be a 1, that must be a 1. 1 in box 6 is in one of 2 places, perhaps. These 3 squares here have got to be 3, 4 and 5 to complete the 12 cage. That can't be a 4, that can't be a 3. That one we don't know about. 6 at the bottom of the grid is resolving the 6 and the 8 over here. And the 4 and the 6 on this side as well. The 8's bouncing back over here, resolving the 8 and the 3. Good grief. Right, those 3 squares now are a 2, 3, 4 triple. Now, that 4 sees that square. This 4 sees that square, so that's a 4. There's probably more we can do there. What are those 2 squares? 5 and 9. Is that not resolved? I'm not sure that is resolved. It sort of feels like it might be, but I can't see why immediately. What about this column then? We've got loads of digits here. We need 5s. Yeah, okay. Where does 8 go in this column? It can't go there, so that must be an 8. That means 8 is exactly in this square. Now this square is now a 1 or a 9 by Sudoku. And unfortunately, I can't see whether we can resolve that. We probably can, and I'm missing it. This square's a 5 or a 9. So these 2 squares have got to be 5s, 6s. Yeah, this is useful. So now we should ask the question about this column. Where does the 6 go? This can't be a 6 because there's a 6 in this cage already. This puzzle is absolutely superb, which means this square is a 5 or a 9. And this 6, via the medium of madness, sees that digit in its cage, so that's a 9 and that's a 6. This 9, via the medium of madness, sees this square, so that's a 5, that's a 3, that's a 2, that's a 3. Oh, keep going, come on. 5 and 9 go in the grid. That square's got to be a 9. That 9 sees the 1 over here. That's a 9 now. Let's get rid of the pencil mark here. Now, what are those 2 squares? They are a 1, they're a 1, 2 pair, and there's a 1 at the top of the grid. So that's 1, that's 2. 2 is in one of these 2 cells. That's no longer a 1. This 5 is seeing that square, so that's a 3. Well, that square, I should be able to get that square. That's true, isn't it? So that looks like it's a 9. This is a 4 or a 5. Okay, and it's not 4. So that must be the 4, that must be the 5. And that means that's a 5 as well. These 2 squares are 2 and 6. And the 6 here sees the 6 there, or the potential 6 there. So the 6 goes there, the 2 goes there. These squares here have got to be a 3, 4 pair. We can do that. That fixes that as a 5. Or really, it was fixed by that one, I suppose. But I was slow. Now it's got to be a 1. Now, we're going to have to check all these cages as we do this to make sure we've not made a ricket. So this is a 3, 9 pair, and that means that's 3, that's 9, that's 9, that's 6. Let's check this cage. That does look like it's got all the digits in it to me. So hopefully that's correct. Now these 2 squares have got to be 4 and 6. There's a 6 here, so 6 and 4. Let's check this cage. Yeah, that looks good, doesn't it? And that means those 2 squares are 2 and 5. That's 2, that's 5, and that is, yes. Oh, I tell you what, that is one of the great Sudoku puzzles. Tom One Eye, take a bow. I do not know where you have emerged from, but it is from, you've immediately sort of, I don't know, springboarded yourself onto the podium of magnificent Sudoku setters. That is absolutely ridiculously clever. From the break-in was quite, it was clever but not ridiculously fiendish because it was quite well signalled. So getting that all of the orange squares were different was really very beautiful. But then from there, you went sort of down a rabbit warren of complexities and these interesting little nuggets, like there had to be an 8 on that diagonal. I remember I got that. I can't remember at what exact point. I worked out there had to be a 7 on a 10 diagonal. Oh, yeah, this 55, the selection of 55 as the correct sum for this diagonal is one of the great moments in Sudoku, because the fact that you had to force an extra low digit into one of those 4 squares as a result of the 1-2 pairs is just a beautiful observation. It really is. And that's to then constrain these squares to being 2s, these squares to being 1s. I can't quite remember what that led to, but yeah, but then there was the stuff around 8s in the corner and 6s in the corner over there, and the way they bounded or bounced around the grid. This square was fascinating, wasn't it? And the way it sort of led to striping in those squares, and that it forced itself twice into box 2 if you selected the wrong option for it. That was also absolutely gorgeous. It's just full. It's just replete with gorgeousness, this. It really is a stunning, stunning Sudoku. I hope you enjoyed it. Let me know in the comments. I do enjoy reading them, especially when they're kind. And about this puzzle, if not about my solve, they really should be kind. And we'll be back later with another edition of Cracking the Cryptic.